As a next step, once we have parsed all the instructions into a program, our assembler is going to do some layouting. It's going to figure out at what addresses each instruction needs to be, and it also is going to figure out the encoding of the individual instructions. And so it would be good if we had a way to print the parse program, or print the assembly in general, back out to the terminal such that the user can inspect it. And if it has additional addressing or encoding information, that we have a way to display that. So I think what we want as a next step here is we want to create an assembly printer, which is basically the opposite of the assembly parser and has the ability to regurgitate the program back at the user. I think we want this kind of usage model where we can create a printer object and we give it the entire program we want to print, and then it has a print function that just turns the entire program into a string that we can then spit out. And maybe let's do this like this, a bit more compact. Okay, so assembly printer hasn't been defined, so that's next on our to-do list. So right here after the parser, let's add the printer. It's going to have a program variable, which is non-optional, so we need to supply it with a program to print. And so what we need to implement here is the print function, which is basically doing something with the program and then returning that as a string. So this needs to be a data class. And there you go. It's currently just printing hello, which is in here, but that's what we want to change. And so essentially, I think what we want to do is we want to create a local variable that contains the output that we're gobbling up and kind of producing. And then we just want to go over each instruction and print each instruction and then return the output that we've created. So we start with an empty output. We go through the program and print each instruction. And then we clear the current output and return whatever we created. All right, so that's now failing in the parse instruction function, so that's the next thing we need to fix. It's actually supposed to be the print instruction, so the print instruction function is now the next thing that is missing, so let's add that. All right, so let's get started. What's the first instruction in our program? It is an LDI instruction. So let's figure out how to print LDI. I think we want to have a few functions that we can call that just do the generally right thing for the printing. So we want a print opcode function that just prints, for example, LDI here, and then a print operand function that just prints the operands. And we probably also want an emit function that just prints some random text. And then at this point, I think we're basically done. And if something is not an LDI instruction, let's just emit the raw instruction object. And then in any case, we want to append a new line. All right, that should print at least the LDI instruction, and then all the other instructions just as a kind of object representation. Cool, so the next thing is print opcode. All we want to do here is basically print the text we were given, but indent it a bit, such that we have this format here where we have a few spaces to the left of the opcode to distinguish the regular instructions from the directives and later maybe the labels. 1, 2, 3, 4. Okay, pretty neat. So next problem is we don't have an emit function. That should be pretty easy to fix. We just append whatever text we're given to the output. And that seems to work. We're now stuck at print operand. So if this is an immediate, we just print the immediate as a integer. If it is a register, we just print the R for the register and then the register index. And then the register pair is just going to be the base register and then the base register plus 1. Let's see if this works. Cool, that actually does seem to work. That does do something. And so what we print out is LDI, which is pretty close to what we had in the input here. And then move, we don't have any of the printing implemented, so we just get kind of the raw object that we have in the assembler in the background. And then basically all the LDIs are easily visible. So let's go through the instructions and implement some printing for each. This should be fairly straightforward. I think first up, let's do a NOP. Let's maybe actually create the new line up here in the loop, such that we can use a return here, make our lives a lot easier. All right, so NOP is just printing the NOP opcode and then returning. Let's see if we can see the NOPs appear in the output. And yeah, there they are. That's pretty cool. Next up, we had a move instruction. The move instruction is just going to be printing its two operands like we did for the LDI instruction. And indeed, that seemed to work. Then we had a absolute jump with only a single operand, which was a register operand. And indeed, that worked. Next up, we had jump relative with immediate. That should work just like this. And indeed, that did work. There's our jump relative with immediate. And there it is down there. One thing we can do is to make the output a bit easier to look at is we can add a plus sign to the output here to make it clear that this is a relative jump based on the current program location. We could add a hint relative Boolean flag to the print operand function, which helps print the integers in a special way. And by default, it's just going to be disabled, but whenever we print an immediate, we can prefix the operand value with a plus. Let's see if that works. There's a comma missing. And there we go. So this is the same as before, minus 32. But the jump forwards now has a plus 18 there, which is kind of handy. That's pretty cool. And I think another thing we can do to make these things easier to read is to allocate a bit of space here in the beginning for the opcode and not immediately start with the operands right after the space. So for example, we could allocate 7 characters for the opcode and then have it left aligned and fill everything up with white space. And this looks like this now, where we have a good separation between the opcode and then the operands, which I think it's pretty neat. All right, what other instructions are missing? There's a jump relative with register, where we don't have this hint here because it's a register anyway. And that made this work here. Then we have the pseudo instructions. Pretty simple, it's just a halt. That worked. And we have the directives. And so for the directives, I don't think we want to use the print opcode function because that inserts indentation. I think we just want to print the .org. And then followed by the operand. Return here. Okay, that seems to have worked. There's actually some org in the output. I think we want another one of those hints where we basically hint the printer for the operand here and tell it that this is actually an absolute address that it should display. And so if we are printing an operand and the address hint is set and it's an immediate, then let's use some hexadecimal notation for it. Let's see if that works. Yeah, pretty cool. So this properly prints out the address that the org directive was given. All right, so this is pretty cool. Basically what we can do is we can parse an assembly input, and we're making sense of whatever is there and ensuring that we understand all the instructions. And then we have a method to actually print it back out to the command line output. And it basically formats the instructions again with all the values that we've understood. And it's quite readable the way it is right now. So we read assembly and we can write it back out. One of the first tasks of the assembler is going to be to actually assign absolute addresses in the output binary to every one of these instructions. And it would be cool if we had a field in the instruction object that actually stores this address. And if the assembly printer that we've written here sees this field, it should actually print the addresses that we assign to instructions in front, so we can actually see what the assembler is doing. So let's go and add that. I think on the instruction we want an optional address field that is just going to be set to none by default. And then when we do the assembly printing, right at the beginning, I think we want to look at all of our instructions, and if any of the instructions contains addressing information, I think we want to set a Boolean flag that basically says, okay, we're going to print address information in the output. So if any instruction address is not none for any of the instructions in the program, then this flag is going to be set to true. And what this allows us to do is if there's no addressing information at all in the program, because it hasn't been laid out yet, we don't add a address column here in the output. But if there's some addressing information present, we can actually include it in the output. And so the way I think we want to do this is, I think we want to prefix the instruction with this addressing information here in the instruction printer. So if the emit address is set, we just set it to question marks in the beginning because instructions might not have any addressing information set. So in that case, we want this to actually show. And then if the instruction actually does have an address, we want to use that address as a string here. And then finally, we're just going to add the address as a prefix to the current line. And so what should happen now is this shouldn't have changed any functionality in the printer. And sure enough, nothing changes. But now what we can do is, after we've parsed the assembly and we have parsed a few instructions, we should be able to go into one of the instructions and just assign a random address there and then see it pop up here in the output. So let's say instruction number 4 gets a random address assigned. And then let's see if this actually shows up in the output assembly. Okay, that looks promising. So we get this address prefix here in every line, but most instructions don't have an address, so there's a question mark. But if I scroll up, the instruction at index 4 has its address set to hex 1234. That is pretty exciting. So whatever we do in the assembler, if we write some code that does the layouting of the instructions, we can actually observe that it is doing this because it's going to include this information in the output, which is pretty fancy. And I think we want to do exactly this now. Instead of setting this address manually, I think we want to create the layouter class that can take a program and basically go through it and assign fixed addresses to each of the instructions. So that's how I want this to work. I want to be able to create a layouter object and then ask it to lay out the program for us. So let's do this. And so what we need is a layout program function. And all we have to do is basically go through every instruction in the program and call a layout function on it. So how do we lay out the actual instructions? I think we need a variable in this layouter which basically stores the current address in the binary where it's currently positioned. And then as we step through the program, every instruction is basically increasing this address by the number of bytes in the current instruction. And right now this is always 2 bytes because we have pretty simple instructions. But maybe in the future we have compressed instructions where some instructions only take 1 byte. And so this layouter would then take care of that. So we have this current address here that starts at 0 by default. And then instructions just trivially take the current address and store it as their own address, and then increment the current address by 2, such that the next instruction in line is properly positioned after the current one. And so, quite honestly, this should be all that's needed to go in and go through the program and assign addresses to the instructions. Let's see if this works. Cool, this actually does do something. So if we scroll all the way to the top, we start at address 0 for LDI, and then the move gets assigned address 2, the next one 4, 6, 8, etc. And we just go through this and we just keep assigning new addresses and we just keep bumping the address by 1. Now we have a special instruction here. We have this org directive, which we want to actually influence how this layouting happens. Whenever we see an org directive, we actually want to use this value that we provide in the input and change the current address to this value, such that the instruction after the org directive gets this new value as its address. So let's see how we can do this. All we have to do is check if the current instruction is the org directive and then do some special handling there. One potential issue in the input that we can have here is the org directive might actually indicate an address that is too low. So let's say, for example, here we've filled in a few instructions and then we're at this jump relative with immediate instruction at address E. And if the next org instruction says, oh no, I actually want to have the following instructions be at address 6, we should throw an error because there's no way how we can go back and overwrite these instructions. We don't just want to kill instructions. So org should always just be able to kind of create big gaps to an absolute offset in the program. But we want to emit an error and indicate to the user if the org directive would actually start overriding existing instructions. So in case this org address doesn't line up and the org address is actually behind the current address pointer, we throw an error and exit. If this checks out, we're just overriding the current address value to whatever the org directive is telling us to. And then we set the org directive's address to that same address and we just return. We don't do anything else. Let's see what happens. That looks very promising. So if I scroll up, we have these instructions starting at 0 and then counting up. But then at the org directive, we see the address jump up to hex 20. And then the following instruction here, the LDI, is actually starting at hex 20 and then keeps on going. And if I scroll further down, we have an org that puts us way in the back of the binary. And as you can see, this actually worked. And the remaining instructions here are positioned at this F040 location. That's pretty cool. So let's see if we can trigger this error somehow. One approach would be to change this org directive here. So this HALT instruction is at address 3C. So let's say we want to have org here place us back at address 30, which is way up here in the middle of the instructions. And that seems to be a problem, but we don't have this error function implemented. In fact, the error function was actually defined on the assembly parser class, and it produced this nice colored output plus some text output. So I think we want to factor this out into a error helper function out here that we can use from other places other than assembly parser. And so what we want to do is, first of all, just display the error message with this red coloring that we've set up here. So we're going to reuse that. And we also want to accept a variable number of arguments to this error function. And these arguments, they can be just strings if we want to have additional lines of text being printed with the error message. But maybe it could also be an instruction object, and then we want to print that instruction somewhat nicely for the user to see. So we go through the arguments. If one of the arguments is just none, we don't do anything. If someone passes an instruction, I think we just want to pretty print the instruction and show that as part of the output. And we're going to use a little trick here. We're going to create a fresh new assembly printer with a program that consists only of this instruction that we were given to include in the message. And then we'll just print this and then include this as part of the error message. And then otherwise we just print this as a regular error line. And finally, we also want to exit. That is pretty cool. So if we rerun our assembler, we should see a proper error message pop up. And sure enough, it does. Org directive address is behind current address. So that seems to be working. Let's see if we can pass the instruction to the error function and have that printed. That also seems to work. Pretty cool. So we also get to see what exactly the org directive was that caused the problem here. So let me return this back to the functioning version. So that works again. And then let's create a syntax error somewhere in here. For example, we could create an illegal register pair, and let's create an error message. And then let's see if we can make the parser reuse this new error function. So instead of doing this manually here, we will just call error with the error message. Alright, so this should print the error message just like it did before, just with the new error function that we've defined. And indeed, there's no change in the output. That seems to be working. So let me fix this again. And it's back to operational. That's pretty sweet. So I think in terms of layouter, this is all we really have to do because we don't have any fancy instructions yet, and this org directive is the only directive we currently support. But in the future, you could imagine that there's different directives we want to have. There could be a relative org directive that just jumps a few bytes forward. But we could also have a directive that's called .0, and it takes a number like 42, and all it does is insert 42 0 bytes. And then that instruction would advance the current address not by 2, but by those 42 0 bytes that it wants to insert. But I think for now this works out. Thanks a lot for watching. Like and subscribe if you want to see more of this, and see you next time.